Okay, hi everyone. We're going to get going today. The wireless mic is not working today, so I'll project. Let me know if in the back, if you're having trouble hearing me, just raise your hand since I've been using the microphone up till now. Normally in this lecture hall, I would just project. The mask provides a little barrier. I put some notes up here. Lots going on. Midterm is scheduled. A couple of people have already asked me if you do have some conflict or something, probably you'll have to submit a petition to resolve what's going to happen with that. But that's during our tutorial time, so most of you should not have any conflicts there. And problem set 3 we're going to post this week, and it's on a topic which we haven't started yet called instance centers. And instance centers is going to be one of our first methods of systematically figuring out how mechanisms move. And in particular, it's going to allow us to better visualize individual link rotation within a mechanism. And a lot of you have been asking me questions. This may look familiar from the problem set about limit positions. And I ask you things like, I think this is the first problem, find where the output C has max speed. And I ask you things about limit positions and whatnot. And the common question is, I can't visualize the motion. What's going on here? And so my suggestion for you, until we get to some of these other techniques, like instance centers and more rigorous velocity analysis and whatnot, when we're going to be able to sketch things out as vectors and equations, for now, and I include this as a question before teaching those rigorous methods, because I think you can do this already, I'd like you to think about individual links and connections. So these are links. I think it's the same numbering is on there. 1, 2, oh no, it should be 3 here. And this guy's 4. So you have some tools like kinematic pairs. I suggest you think about each combo of pairs. Every link that's touching another link, write out what the kinematic pair is touching, how they're connected. So that's my first suggestion. Anytime you're not sure about how a mechanism is moving, half the time when I talk with students who aren't sure about what's happening, they made some wrong interpretation of the basics. So think about the basics. If there's a lot going on in one spot, isolate that piece of the mechanism. Like 3 and 4 and 2 are all connected there. So why don't you draw link 2 and link 3 off by themselves like this? That's a great way of isolating what's happening and thinking about, okay, when I draw it like this, we can see that it's just a turning pair connecting link 2, which is going round and round one way or the other, to link 3, which is just a block. Okay, so go through all these combos, make sure you understand how they're working. Then the next step, and I'll take your question in a second, sorry. The next thing after visualizing motion of these things is finding limit positions. That's a lot of what I'm asking you to do. Limit positions. And I hide some questions. In some questions are hidden things like limit positions. Things like max or min velocity. Those have to do with limit positions. So that's my, my hint to you. But how do I find them, right? I didn't teach you how to do it rigorously. But I mentioned to you, look for parallel or perpendicular arrangements of links. Almost always, that's where something special is going to happen. It's like a maximum of a motion. So for this mechanism, I would suggest this is a nice one because the geometry is pretty simple. You have link 2 is going round and round, and link 4 is going back and forth. That's really all that's happening here. So link 2 is the only thing that has an angle changing. So where we have this long axis, that's really the only axis of interest. And then there's like up, down, left, right. So I would suggest you actually sketch out the mechanism and try out some candidate drawings. Here's link 2 in the vertical position. Okay, and I would try vertical, right, down, left. And you could try parallel or perpendicular to this axis. That's like this sliding axis. Just do a quick sketch of each one. It'll take you 2 minutes to sketch out, what is that, 4, 5, 6 or 8 options off to the side. And once you do that, you can try and sketch the whole mechanism on there. Once you do that, you can ask yourselves, is one of these clearly the limit position? And I think once you do that, if you don't find it, obviously, you'll probably narrow it down to 1 or 2 right away. Clearly, one of them is to the right, you can ask yourself, okay, which one is more to the right on the output? Okay, so that's my suggestion for limit positions. Draw out a bunch, trial and error. It doesn't take too long. We have our stick diagram notation, so you can draw them real quick for yourself. Any questions about this problem? There was one question here. C is this point on the link for. Any other questions about finding limit positions?
Not for question 1, but for question 2, can you explain the setup of the question? Because it says it's a constant rotation, but it's a rocker-rocker mechanism. So
okay, so this is a question about problem 2, where the input, okay, I'm asking about limit positions, and there's I'm visualizing the mechanism. There's a bunch of links there connected, and hint, there's a 4-bar in there. You probably saw that, and you can identify which type. And when you do, it might not make that much sense of the question. That's what you're asking about. Because I said that it's a constant input. And the reason that I mentioned constant is because when we're doing timing ratio, remember for timing ratio, in lecture I drew out this nice plot for the slider crank mechanism. Different mechanism, but we plotted this out, and we found these limit positions were like the max x position over time, maximum x position. But we assumed that the input was going constant, right? And so in that mechanism, the input could go round and round continuously. Other mechanisms, like a rocker-rocker, the input has to turn around and go backwards. It oscillates, the input. But it's still important for something like calculating timing ratio, which I ask you to find. Timing ratio, right? You need to know how fast the input is going during that motion. So I say it's constant. So whenever it's moving at the same speed. That'll allow you to calculate timing ratio. Okay, any other questions about our previous material? Okay, so our topic for today is continuing from the video lecture which I posted last week. Thanks for the well wishes. My sore throat went away the next day. Most years I would not think anything of it, but this year, right, I'm not coming in if I have a sore throat. If you didn't watch the video, please watch it right after this because it's going to fill in some of the blanks. I'm going to assume that you have that background, but this is our quick summary of the main points, right? Every point, which is like a point on a link, we're going to think about it like you take a marker and you put a dot on a link, and we're going to track that dot, right? That's a point. They have a velocity. And every link has a single rotation rate. We're assuming our links are rigid. So if my paper is rotating, right, points don't have a rotation rate. That doesn't make any sense. It's a one-dimensional thing. But the whole link can rotate together. And today we're going to start attaching vectors to our links so we can study not just basic points, but actual mechanisms. And I introduced this way that we're going to use to denote vectors in this course. Right? Our standard was, ooh, that is not straight at all. I really enjoy this comically large double eraser. Okay, here we go. Still not perfect, but pretty good. So this is our vector. We're going to use r for position of B relative to something like the origin O. Okay, and it's a vector, so I put this wavy line underneath it. Okay, so our coordinate choice, which is often used for mechanism analysis, is not Cartesian coordinates, but this new type of coordinates I introduced in the video, which align with this axis of the vector. So we have our radial direction, which is I subscript r, and we have our transverse direction, I subscript theta. Right? And you can think about it, if you increase the length, that's r, point B would move in the radial direction. If you increase theta, which is the angle of that vector, point B would move in the theta direction. So hence, radial and transverse r and theta. And these are specific for this vector only. Every other vector would have its own set of coordinates. So we're going to put the subscript on there anytime that it's not obvious which ones. So that's our radial and transverse coordinates, which allows us to write out that position vector as a magnitude, just RBO without a vector underneath it. That's just the length of that vector and its direction. So that's how we express position vectors in this radial transverse coordinate style. Okay, it's similar to polar coordinates, a little different because we're expressing them, it's kind of attached at the end there. And we derived on the video the velocity by taking the time derivative of this, and we got two terms. We had r dot in the radial direction, and we had the transverse component, which was the length of the vector times its rotation rate in the transverse direction. Okay, I'm just leaving the subscripts off so it's a little easier to understand. I'll sneak them in now. BO on everything. Okay, so that's the velocity of point B relative to our ground origin, O. And today we're going to generalize this a little bit because we want to express more than just velocities of points relative to the ground. We're going to have links moving, and we're going to want to express how links are affecting each other so we can sort of step through a mechanism. So today's main topic is going to be, let's do relative velocity. Relative velocity. And we're going to take, instead of just having a point, we're going to take these vectors and we're going to attach them to our links and use it to calculate whatever we want about our mechanism, velocities and positions. So that's what we're going to do. So I'm going to do this same drawing, but I'm going to have 2 points now. So we'll still have our ground down here. That's our origin base point down there, just as a reference. But now we're going to have 2 points. Let's have A, and over here we're going to have point B. Okay, and those are moving through space. Last time I kind of put these wavy lines, like this is the path of A. Just kind of making up a path for each of these points, just to indicate that they're moving through space. Okay, and we're going to be interested in the relative motion between A and B. So let's say our ultimate goal was to get the velocity of B. Our trick today, or our method of mechanism analysis, is going to be, let's divide up the position of B into 2 components. So one way of describing the position of B would be one vector from the ground. We'll call that RB relative to O. Okay, but now we're going to divide it into 2 pieces. We're going to step through A. So first we're going to say we could have position of A, RA. Okay, and added to that now, we're going to complete this triangle. And this is going to be position of B relative to A. So that's our language. The first subscript is where the vector is pointing. And the second subscript is where the vector is coming from. So we'd call this position of B relative to A, RBA. And yeah, okay, RA relative to O is what that is, really. Sometimes we won't express, right, if we have something relative to the ground, sometimes it's kind of implied that RA means RA with respect to O. That's kind of implied oftentimes. When in doubt, you should write it out completely, RA with respect to point O. Okay, so that's our position. We can take time derivatives, just like we did in the last lecture, and get velocities. Now, everything is just linear with these equations. There's no like quadratic terms or anything like that. So taking velocities is as simple as just changing all the r's for position to v's for velocity. So we can do the same thing for positions or velocities or later accelerations. if we want to find the velocity of B, we can step through point A. Okay, and this seems abstract for now, but in a little bit we're going to basically connect these vectors to links in our mechanism. And these points of interest are going to be our turning pairs or sliding pairs through our mechanism, and we're going to draw some vector expressions for positions of velocities graphically, and then we're going to write out their equations. Okay, this VBA, right, we can just swap in any subscripts here. So this is velocity of B relative to the ground, but if we're talking about velocity of one point relative to another point, we just substitute A in for the ground. So the equation on the other board, I'm just going to repeat it here with A instead of O. So there's our radial component. And there's our transverse component. Okay, it helps to write a little bit larger. These get a little awkward, right? We have double subscripts going on here. So make sure you're writing clearly. I'll do my best as well with my limited board space. Okay, any questions about this? Pretty basic, setting up these relative vectors. I want to do it nice and careful like this, because now what we're going to do is start attaching those to the links. And in fact, I'm going to identify two special cases for links. And it's going to become clear why this radial transverse coordinate set is really handy for real mechanisms with linkages. Okay, so these are our two special cases. And this won't allow you to analyze every mechanism component, but it'll allow you to analyze many. Okay, and these are special cases when we're using radial transverse coordinates. Okay, so case one, and we're going to refer to this a lot, case one and case two scenarios. So I'll give you the definition. It's just 2 points on the same link. Okay, and that's going to happen all the time in our mechanism analysis. So I'm going to draw a link here. Just to be a little more clear, I'm not going to do a stick diagram. I'm drawing just a full link. And let's say it has these 2 points A and B. Okay, let's say I want to transfer motion through this link. This is my link body. We'll call it link 2. And let's say I wanted to express velocity of B relative to A. Okay, let's say I already know the velocity of A somehow. Maybe it's connected to the ground, or I've already calculated it. And I want to calculate the velocity of B. I can use this. This is this is our relative velocity equation up here. So we can use that to step through. We're trying to find velocity of B relative to A. So I can look at my equation. It's all the way up there. Can't quite point to it. We have r dot. That's like these points getting further away from each other or closer. Right? I'm going to actually draw that vector on here. This is our r vector. Okay, and it has some angle to it. I'll call it here theta BA. Okay, so looking at our equation closely, r dot, it's a scalar quantity, r dot BA. That's the rate of change of the lengthening of this vector. But if these 2 points are on the same link, and it's a rigid link, that tells us that the length is constant. So r is constant. And if r is constant, that'll tell us r dot equals 0. Okay, simple concept. Link is rigid, 2 points on it. They're not getting further away from each other or closer to each other. So that means that whole radial term goes to 0 in our equation. So we can express VBA. It only has the single transverse component now, which is r, that's the length, times theta dot. And it's in the transverse direction. I'll add my subscripts, BA. Okay, and as always, when we write an r vector, we can immediately put these radial and transverse coordinates on it. Radial goes out along the length. Transverse is 90 degrees counterclockwise. So that's the transverse direction. Okay, so that allows us to calculate velocity of B relative to A. Okay, and this is our case 1 conclusion. Transverse component only. Okay, and that should make sense. Imagine if A was not moving, like it was pivoting around the ground, a ground base pivot. B would be moving at this instant perpendicular to RBA. Okay, any questions about this? This is our case 1. It's pretty straightforward, and we're going to hunt for these in our mechanism analysis because they're really easy. Always transverse direction, really easy to just put them up on there. So I'm going to look at a quick example with you here. This is going to be our first mechanism full velocity analysis. We're going to do a 4-bar, and it's going to have a little extension on link 3. So let's sketch out a 4-bar. Okay, try and draw it similar to mine because the shape that you draw it affects these velocity vectors and everything. And by coupler point, I mean link 3 here has an extension on it. So this is my extension point, and I'll call that point C out there. And these other pivots are B and D. Okay, so link 3 just has this extension attached to it. We've seen some 4-bars like that before. And this is going to be our first analysis problem. So let's assume we know some input. Let's say we know the rotation rate of link 2 as an input, theta 2 dot. And let's also just assume for now we've already calculated the other rotation rates, theta 3 dot and theta 4 dot. So let's say we've calculated those already. Let's find the velocity of that new point C. Find the velocity of that coupler point C. That's our task. Okay, we see that we have 2 ground connection points. So for velocity analysis, we're always going to start at one of the ground connections somewhere, because we know the ground has velocity of 0. So I could name these points like O4 and O2. Different ground origin points. And all of those ground connection points have a 0 velocity. So we can start our analysis at either of those. And we're going to try and step through our mechanism and use case 1 examples to build up our velocity of C. And so you'll have 2 choices here. You can start O2 or you can start at O4. I'm going to choose O2. It's physically a little closer, easier to draw. So we're going to step through point B. So we're going to write out an expression similar to what we wrote on that original relative velocity expression that splits the problem into 2. So we're going to try and find velocity of C relative to the ground. And I'm going to study O2, so I can put a 2 there if I want. And I'm going to step through point B. So we'll say First, let's find B relative to O2. Then let's find C relative to B. Okay, just building it up in two pieces. Instead of B, you could have used D, and that's like going through link 4. That's an alternate solution. You can try that on your own later. So first, let's study that first piece. That's velocity of B relative to O2. And if you just look at the mechanism, you can see B and O2 are both on link 2. So that's the key. So B relative to O2, that's what we're trying to find. B and O2 are both on link 2. Okay, so as soon as you identify that, which you'll get really good at identifying these, you can say this is a case 1. A case 1 scenario. 2 points that are on the same link. That's going to allow me to write my velocity B relative to O2 really fast and easy. It's this one here. So we're going to sub in B, and instead of A, we're going to have O2. So we're going to have the same expression. Okay, and this is going to happen all the time in our mechanisms, because we're going to step through mechanisms in the same way all the time. So you're going to memorize this, our case 1 equation. You'll use it over and over again, and you can just sketch it out. So we need to kind of interpret these different pieces here, right? RB relative to O2, that's like the length of link 2, right? Or we could call it R2, length of link 2. Okay, theta dot B relative to O2. I haven't actually drawn the link out, right? Let's do that. Here's link 2. But we've done it before for various links. So right attached to the link, that's our vector. Okay, and it rotates with the link. So we could say this theta dot, that's the rotation of the whole link. Okay, any theta dot that has to do with 2 points on the same link, that's going to be just rotation of this entire length 2. We would call it theta 2 is maybe the angle of that link. So this thing we could rename theta 2 dot, rotation rate of link 2. Okay, and the last piece is the direction, which we've already found. Radial would have been out along that vector. But we want transverse, which is 90 degrees counterclockwise. So that's our transverse direction. Okay, I'm going to put it up on the original diagram here. Okay, so it's perpendicular to link 2. And if theta dot is positive, that means this angle is getting bigger. If theta dot is positive, and the velocity will be down and to the left. If theta dot was negative in our equation, that means this angle theta 2 is getting smaller. That means the link's rotating clockwise. And this is still correct, but it's a negative sign on it. So it would point the other direction. Okay, any questions about this? It's our first velocity piece. Step 1, yeah.
So like, in case 1, the velocities of points are always perpendicular to the radius?
Yes, case 1, the velocities are always, you choose your 2 points, connect them with that vector, and go perpendicular, counterclockwise. It's always going to be like that, regardless of the link shape. Our next link, link 3, is a weird shape, so we'll see what happens there. Other questions? Yeah, Kai.
Sorry, I think you already mentioned earlier we're allowed to use either O2 or O4.
Yeah, so I chose, the question was about O2 was the choice I took. You could have started at O4, and then we would have had a different expression here. Give it a try. You would have done velocity of D relative to O4 plus velocity of c relative to d. That would be an alternate solution method. Stepping through point D instead of B. And you could check your work that way. Yeah.
Right now we're just looking at O2 and C because that's what like the question asked for, just to
Yeah.
find BC. But what if there were more turning points in between those 2 points? Could we expand this to go through, instead of just going through B or just going through D, could we go through B, F, C, and
Yeah, great question. This mechanism just required one step, going through B first, and then we get to C. If it was a more complicated linkage if you had a 5 bar and you needed to go through another point, you just make this equation longer. Just add more relative points on. Yeah, and we'll see examples of that later. Let's move on to our second step and may answer if there's other questions. So we did B relative to O2. That's the first half of our split. Now let's do velocity of C relative to B. Okay, and I'm going to move over here. Okay, C relative to B. We identify those are both on link 3, right? Both C and B are on link 3. So that's the first thing to notice. Link 3 is a weird shape, so it's a little less obvious maybe. But think about your points. And this, of course, is another case 1. So that's great. We love these case 1s. We're always going to try and build up. But you have the choice of how to design this analysis. I chose to start at O2, go to B, and then C. And I chose that because it led to 2 case 1s. So here's another case 1. So we can write that immediately. Let me put it over here. Okay, I can just go immediately. I've memorized my relative velocity equation and just substitute in the correct subscripts. So this one, sorry, is there a mistake in it? This one is no dot. Thank you. Here I am all proud of my memorization. Thanks. Yeah. Distance, that's the length, times the rotation rate. Thank you. Yeah. So now interpreting these is a little trickier because it's not clear where those vectors go. So let's actually draw out that link 3. Okay, so here's our link 3. I'm going to move that out of the way. So C and B, those are the 2 points that we're studying, right? C and B. So nothing changes from our analysis before. So think back to this one. We're going to draw a vector connecting B to C and go from there. This one's weird. We're not going to go along this. The shape of the link doesn't matter. All we care about is points B and C. We've already identified their case 1. So just follow the case 1 rules. Let's draw a vector connecting them. We call that our CB. And you don't have to do this every time, but anytime you have a weird shape link, until you get really comfortable with them, I suggest you draw this out so you can figure out what's happening. So that length of that vector is RCB, right? So you can measure this distance. If it's a graphical problem and I give you a scaled diagram, get your ruler out, measure that distance on link 3. That's RCB. Theta dot, that's rotation rate of the whole link. It's always going to be that. Now the last piece is the direction, I theta. It's tempting to say, okay, it should be perpendicular to this segment or perpendicular to this segment. Nope, we don't care about those. We don't care about D. All we care about is C and B. And we already put our vector on. So let's just go perpendicular to that. That's our direction. Okay? So this is really all there is to it. We basically have finished the problem now. You would add together our 2 equations. Equation 1 and equation 2. Okay, and if it's a graphical problem and you wanted to give actual numbers in here, you could measure all these things, right? You're given the rotation rates, theta dots. The distances you could measure on the diagram, or they'd be given to you maybe. And these directions you could measure on the diagram as well. And you would get something that looks like, let's sketch it out. Let's sketch it out. It's going to be down and to the left. Okay, that was BO2. And on the end of that, we're going to add this new one, which is up and to the left. So you could actually graphically draw these out as vectors. This is maybe the clunkiest part of this process. Right? Once you get these as answers, we're kind of relying on this graphical method. You'd have to sketch these things out. And you could sketch them out in a scaled sort of velocity diagram like this. And this is what we're going to actually do in an upcoming topic. We're not going to do it rigorously right now. You can just keep it as a rough idea right now. We're going to call these things later velocity polygons. So stay tuned for that. Basically, next week, we're going to be doing that in a rigorous way. And we're going to lay out a whole velocity analysis problem. And we're going to build up these summation of velocity vectors. That's our relative velocity equation sort of visually depicted. And we'll be able to measure our total velocities on that. For now, I'd like you to remember these basic elements and our overall solution approach. Other questions? Yeah.
When we're reporting the answer VC, if we just write them out as the sum of what we got for equation number 1 and equation number 2, if we did have numbers for everything, would we leave the I chapeau theta VO2 as just that? Like, how do we convert that into a numerical value? That's just the direction, right?
Yeah, so the question was, how would you express this as an answer to someone? Like, this is a correct answer. You could write that, right? And you could say, those are indicated. Those directions are on my drawing, right? But they're weird angles. So if you added that up, it's not that usable. So you could use this kind of addition and convert them to Cartesian coordinates, or convert one into the other style, or whatever coordinates you want to express your answer, and you could do that later. And that's what we're going to do in velocity polygon method, which I'd like you to just put a pin in doing that for now, or you can brainstorm how you do that yourself. But you're right about that. Another question.
For the direction I, is it always perpendicular to the position I because of the
Yeah, the question was about I, in particular where this is the transverse coordinate, always perpendicular to that vector. That's just the definition of radial transverse coordinates, always perpendicular. Okay, so this was case 1, right? We solved this whole problem by case 1. And basically we were able to do that because there's no sliders. Sliders, anytime we have something weird like a slider, is going to mess up our solution. So I'm going to, in the last 10 minutes here, we're going to look at case 2. And case 2 is going to tell us how can we deal with a sliding interface. And we're going to have to be a little bit clever in defining our case 2. It's a little bit harder to handle than our case 1s. Okay, so we're going to look at sliders on a slide. And I'm just going to draw you a little bit of a mechanism so that we can study this. Okay, so this is our simple mechanism. It has link 2, which is rotating around this base pivot point. I'm going to call the base pivot point A for this discussion. Okay, and let's say we're given some info about this. Let's say we're given the rotation rate of that link 2, theta 2 dot. So the angle of link 2 I'll define up from the horizontal like that. So let's say we're given that. And link 3 is like a little collar that's sliding up and down on link 2. So let's say we're given the sliding speed and the direction of the sliding, up or down. So you can imagine 1 meter per second sliding up the link 2. And our task is let's find the velocity of the slider of something on link 3. So link 3 is sort of rotating and translating at the same time. So this is a difficult combo, right? Rotation plus translation, there's a lot going on there. So just like we did with our case 1, we're going to break up the solution into 2 steps. And our trick that we're going to pull, and this is what I suggest you do for every slider case, is let's define a special pair of points right here. So we're going to define a pair of points, 2 points, right at that location. We're going to call them points B. And I'm going to draw the links over here so we can visualize what's happening. Let's draw link 2 off by its own here. Okay, down at the bottom is point A. And halfway up, right where I put that dot, on link 2, it's kind of hidden by link 3 over there. On link 2, we're going to put a dot, and we're going to call that B2. Okay, it's like I take this link 2, it's just a rod or a, one straight link. I take a marker and I put a dot on it and call that B2. And it's hidden in here. So B2 is on link 2. At the same time, we're going to have link 3. Let's draw the angle a little better. Here's link 3. It also has a dot. And that one, we're going to call B3. So same thing. I took a marker and I put a separate dot on link 3. And I call that B3. Okay, and both of those happen to be at this instant of time at the same location. So we'll say temporarily occupy the same spot. Temporarily occupy the same position. Okay, and you may say, well, what are the chances of that? This thing's sliding up and down. This is by definition. Like, I'm going to choose these spots. Just like the last problem with the 4-bar, I chose how to do my analysis. I chose to study O2, B, and C. Here, I'm inventing these spots, B2 and B3. And I'm saying at this snapshot in time, they occupy the same location. One is right on top of the other. Okay? And what that's going to allow us to do, by defining those, if we look at our relative velocity equation, I left it up here. Right, this is our relative velocity equation. Maybe if you think, trying to think ahead here, case 1, you remember case 1 eliminated the radial term. Case 2 is going to eliminate the transverse term because r equals 0. Right, if I choose these to be on top of each other, it's going to allow the distance between them, which we'd call r B3, B2 to equal 0. Okay, so that's a trivial statement, right? They're at the same position, so r equals 0. But what it's going to allow us to do is have a simple expression for velocity of B3 relative to B2. And in reality, B3, like at a later point in time, they're not going to be at the same location. So we could say they could have some relative velocity to them. So despite their position being at the same location, we can still talk about their velocity. This is the sliding speed. Right? If B3, that's link 3, is moving up the slide, we could say that B3 relative to B2 has this sliding speed up the slide. So this is going to be our velocity method. We're going to we're going to go back to the whole problem here. We're going to think about how we can, I erased the wrong chalkboard here. Can't show both of them. Let me just erase part of this one here. So we're going to divide our solution into two. So if our goal is to find velocity of B3, let's divide it into two easy pieces. And I'll tell you they're easy, and you'll see why in a minute. First, let's find velocity of B2 relative to A, and then add to that B3 relative to B2. Okay, so it's the same idea as when we were studying the 4-bar. But in this case, we divide it, our stepping stone is B2. Okay, and the great thing about this is that this one is a case 2. A case 2 where r equals 0. And if you think about the first part, velocity of B2 relative to A, B2 and A are both on link 2. So that's going to be a case 1. That's going to be a case 1. Okay, and we'll actually sketch that out here. So velocity of B2 relative to A, it's a case 1. B2 and A are both on the same link. So we measure the distance between them. We multiply by theta dot. That's the rotation rate of link 2 that they're attached to. And we say the direction is perpendicular. Right, perpendicular up and to the left. Perpendicular up and to the left. That's our direction there. Okay, so that was our case 1. In the second half of the problem, that was our first piece. Our second piece, we basically have already answered this. B3 relative to B2. It's just the sliding speed, right? That's what we said here. All we have is that if r equals 0, we're left with just the radial component. That's our case 2. So this is, you can sort of underline this as your case 2 scenario. 2 points on a slider. You can define them at the same location. And all we're left with is the sliding speed. And of course, it's in the sliding direction, which the direction is kind of obvious. It's sliding along the slide. And we'd call that the radial direction. So the last thing I'll do is I'll just put that direction on here clearly. So there's my I theta B2A. That's from up here. And the sliding direction is just going to be along the slide. Okay, so those are the components of this. These two would be added together to get our total velocity of point B3. Okay, we're out of time here. I know I rushed through the last part here. We'll review this one real quick in the next lecture. And we're going to start doing our first real velocity analysis techniques, which do a full problem, and we'll solve some with real numbers completely through. Thanks, everyone.